Hi, welcome back to Introductory Statistics. We're going to finish out Chapter 1 by talking about experiments and observational studies. So before we do that, though, we're going to talk in general about association and causation. And then we'll talk about confounding variables, and then we'll finally get to observational studies and experiments. And then we'll talk about randomized experiments. So if you don't know, if you're confused about some of these wording, like confounding variables, hang tight. It'll all make sense by the time we're done with this section. But before we do that, let's start with a mini review. So let's suppose that a group of researchers wanted to estimate the proportion of students who support a smoke-free campus. And so you compute the proportion that say yes after responding to an email sent to all students asking that very question. Is that data biased? Not biased? Biased because of wording? Biased because over email instead of in person? Biased because responses may be inaccurate? Or biased because volunteer samples are almost always biased? What do you think? Hopefully you answered E, because that's the correct answer. This is a volunteer sample, and volunteer samples are almost always biased. All right, so now let's turn our attention to the topic of the day, which is association and causation. So two variables are associated if the values of one variable tend to be related to the values of the other variable, or if they kind of move the same. And we'll take a look at some examples. Now, this is where things get tricky, because two variables are causally associated only if changing one drives a change in the other. For example, if I'm working an hourly wage, the amount of my paycheck is determined by the number of hours I work. There's a causal association there. Causation is different than association, and we're going to spend quite a bit of time talking about the fact that just because two variables are associated, it does not necessarily mean that there is a causal relationship between those two variables. Some terminology to be aware of. If two variables are causally associated, then one will be the explanatory variable, and that explanatory variable influences the value of the response variable. In the example I gave with your paycheck, the number of hours you worked was the explanatory variable because it explains the value of the response variable, the amount of money in your paycheck. Okay, we'll spend a lot more time with this. So let's practice though. So suppose we've got a set of headlines here, and for each one of them, I want you to take a minute, maybe pause the video, and identify the explanatory and response variables, if there are some, and ask yourself, does the headline imply a causal association? So remember that the explanatory variable is the variable, it drives the change in the response variable. So let's start with the first one. Daily exercise improves mental health. Go ahead and make a note. Is there an explanatory and response variable implied here? And does this headline imply causal association? Okay, the answer here is that daily exercise would be the explanatory variable. So this daily exercise is the explanatory variable. And mental performance would be the response variable. And the wording here, this improves, definitely implies a causal relationship. All right, let's move on to the second one. Want to lose weight? Eat more fiber. What do we think? Does this imply a causal relationship? Yes. It's pretty, yes. So what is the response variable, or what is the explanatory variable? It'd be fiber consumption. And the response would be weight loss. Okay, what about the third one? Cat owners tend to be more educated than dog owners. The explanatory variable would be cat or dog. So this is a categorical variable. And the response variable would be educational level. Now, does this headline imply causation? Not so much. It just says there's a tendency. It doesn't say that owning a cat causes you to be more educated than owning a dog. Just that there is a tendency. All right, hopefully that all made sense. We're going to keep talking about causation and association. The big takeaway from today is that association is not necessarily causal. Think for a minute about two things that happen in your life that are associated but not causally. And we're going to look at some examples. If you can't think of any, that's okay. But try to come up with two variables in your life that are causally associated. And talk about which one is the explanatory and which one is the response. In your head, or in your notes, or with whoever is sitting next to you. All right, so here's an example. This graph shows the age of Miss America. So we've got two curves here. One of them is showing the age of Miss America, the red one, over the years. So this red line is the age of Miss America. And it mirrors fairly closely this blue curve, which is the murders by steam in each year. This is an example of correlation, but not causation. I can't think of any link by which the age of the Miss America winner could be related to the number of murders by steam in a given year. All right. Correlation, but no causation. This is the energy in the California sunlight in energy per square mile, and the number of visitors to SeaWorld over years. So the sunlight in California is the orange curve. And we can see that it dipped in 2010. And so did the visitors to SeaWorld. So there's definitely correlation here. Is there causation? Maybe, right? Maybe because the sun felt warmer, more people wanted to go to SeaWorld and get splashed, right? Maybe because the sun didn't feel as warm, people didn't want to go to SeaWorld because they didn't want to get wet. So this is a maybe. But it's not, but understand we have to do more work. The correlation itself is not sufficient to imply causation. All right, this one might be hard to read, but the green graph is the average daily precipitation in New York City. And the red graph is the per capita consumption of chicken in the United States. They're definitely correlated, but there's absolutely no causation here. Correlation is not necessarily causation. There's no way that chicken consumption can drive rain, or that rain in New York City is going to affect the pounds of chicken we eat per person in the United States. One more. So this is a graph of life expectancy on the y-axis and TVs per 1,000 people around the world in the x-axis. So when we do a graph like this is called a scatter plot. We're going to talk a lot more about these when we get to visualizing data. But usually we put the explanatory variable on the x-axis, the horizontal axis, and the response variable on the y-axis, the vertical axis. And this guy over here, this R, this is called the correlation coefficient. And the closer it is to 1 or -1, the stronger the correlation. But the reason why I'm showing you this is because this is a pretty strong correlation between televisions per 1,000 people and life expectancy. Now, we all know that watching more TV does not necessarily lead us to live longer because we're more sedentary and may not be as healthy because we're not moving as much. But this graph begs the question, should you buy more TVs in order to live longer? Probably not, because association does not imply causation. Why? Well, because there's probably what's called a confounding variable. And a confounding variable is a variable that is associated with both the explanatory variable and the response variable. And sometimes there's a confounding variable, sometimes it is just coincidence. So when we were looking at the visitors to SeaWorld, the confounding variable might be people's comfort level, right? I can't think of a possible confounding variable for the coincidental correlation of Miss America, Age of Miss America, and murders by steam, nor for the rain and chicken consumption. But when we talk about the TVs and life expectancy, their variable might be a confounding variable. We'll talk about that in a minute. But here's the deal. A confounding variable can offer a plausible explanation for an association that we see. Whenever we have confounding variables, or think we might have confounding variables, a causal association cannot be determined unless we do more work. We have to do more work, and we'll talk about that. So, here's an example. There is a correlation between the money spent on pets and the death by falling down stairs. Rates of death by falling down stairs. What might be the confounding variable there? Maybe it might be pet ownership. Or maybe it might be where the pet sleeps at night, right? Or if the pet sleeps inside, or if the pet sleeps in a crate. Or it might be the age of the individual. So that you get the point here, right? There are a variety of invisible things that might be driving this correlation, or it might be just coincidental. And our job is to realize that we have an explanatory variable and a response variable. And there's possibly a confounding variable that is linked to both of them that may be driving the link between them. And that's the question we're trying to answer. Let's take a look at our TVs and life expectancy. We've got the number of TVs per capita and the life expectancy in countries. What might be a third variable? Maybe wealth. If you're wealthy, if you've got more people, a higher standard of living in your country, more people can afford televisions. This might also lead to a higher life expectancy because more people can afford healthcare. And that confounding variable affecting both values may be what is actually driving the relationship, and we have to look into that more closely. So let's practice. We know we can find evidence that more ice cream sales have been linked to more deaths by drowning. What might be the confounding variable? Participation in water sports? Weather? Right? Weather might well be driving both of those. If it's warmer and sunnier, more people are going to buy ice cream. And if it's warmer and sunnier, more people are going to put themselves in an environment by which death by drowning might occur. About the second one, total amount of beef consumed and the total amount of pork consumed worldwide are closely related over the past 100 years. What might be a confounding variable there? Maybe wealth. If you can afford beef, you can probably afford pork. Same thing with the number 3, right? More people who own a yacht are more likely to buy a sports car. Those are people who have the wealth to indulge in expensive modes of transport. And air pollution is higher in places with a higher proportion of paved ground relative to grassy ground. What do you suppose is the confounding variable there? I'm thinking vehicle ownership, right? More paved ground probably means more cars, which probably means more air pollution. Okay. One of the ways we can begin to untangle these relationships is by paying attention to how we have gathered this information. So an observational study is a study in which the researcher does not actively control the value of any variable, but just observes the values as they exist. So everything we've talked about so far has been observational. We don't get to control the wealth of nations or how many, more accurately, we don't actually get to control how many televisions people buy and then measure their life expectancy. We're not controlling participation in water sport or deaths by drowning and measuring ice cream sales. We aren't controlling any of that. Those are all observational studies. A real life example that we just lived through over the past few years has been early in the days of the pandemic when we were trying to figure out what drove infections. We didn't control whether or not someone got infected with COVID or even their activities. I'm thinking specifically of the choir in Washington. We just observed what happened. Now, contrast that with an experiment. An experiment is a study in which a researcher actively controls one or more variables and measures another variable. So observational studies are almost always plagued by confounding variables. which means they can almost never be used to establish causation. And that is important. And one of the things I want you to take away is that observational studies can almost never be used to establish a causal relationship. As an example to this, a New Hampshire state legislature said that an analysis he's been carrying out since 1996 shows that communities in his state that have kindergarten programs also have up to 400% more crime than localities whose classrooms are free of finger-painting 5-year-olds. Pointing to his hometown of Laconia, the largest of 10 communities in Belknap County, the legislator noted that it has only one kindergarten program in the county and the most crime. Noted that it has the only kindergarten program in the county and has the most crime. So, does having a kindergarten program, more kindergarten available, lead to more crime? That's actually in direct contrast to most educational research, but yet, a few days later, the Texas GOP platform announced that it opposed early childhood education because they indirectly understood association or correlation to be causal. This was an observational study, cannot be used to infer causation. Another example. This is the number of active Facebook users in black and the yield on the 10-year Greek government bonds in yellow. Now the yield is related to the debt crisis, so the question is Facebook use driving the Greek debt crisis? Of course the answer is no. Again, correlation does not infer causation. But it's a common mistake. And Stephen Jay Gould has said that the invalid assumption that correlation implies cause is probably among the most serious and common errors of human reasoning. We are reason-seeking machines. And we look for reasons for things that we see happening. It's what's kept us alive. It's what's allowed us to evolve through the eons. And we still need to remember that causation does not imply, that correlation does not imply causation. And this is just a funny. Okay, so, whoops. Let me go back. Sorry. We're going to start here at the top. Your research shows that A is correlated with B. So, with all sorts of caveats. So given C, assuming D and E, assuming D and under E conditions. So you've got research that has a conclusion based on some conditions. The university PR office translates that to scientists find potential link between A and B under certain conditions, which is then picked up by the newswires. And they say A causes B, who are read by the internets and then noticed by cable news, which now says A causes B all the time. What will this mean? And then caught on your local news. What you don't know about A can kill you. and eventually makes it back to your grandma, who is now wearing a tinfoil hat to ward off A. Just a little funny to close out this section. We'll be back in the next video to talk some more about how we can avoid confounding variables.